What's up, everybody? This is Matt Brown with another IoT hacking video. Today we are going to do some firmware modification on this TP-Link security camera in order to get a persistent root shell on the device. In our previous video, we unlocked the bootloader with a glitching attack and were able to get a temporary root shell, but upon reboot, we would lose access to that shell and would have to perform our glitch again on the device. And so in order to get that persistence on the device, we are going to have to resort to a firmware modification, and that is because of some of the file system types that are being used in the firmware on this device, but we're going to get into those details. First, let's go over and let's review the setup of this camera. And yeah, so let's go over to our workbench here. So you can see that I have a disassembled camera. This camera came as a 2-pack. So I've got this fully intact device over here. Going to set that aside because I have removed the important guts of the camera. And here we have the most critical PCB on the camera. And it's all hooked up to its motor and its power supply so that it will function just fine. And so let's just review from the last video what we have on this board. Okay, I'm going to turn my microscope light on here. And so right here, you can see, let's get that into focus, we can see the main CPU of this IoT camera. And so here we can read that this says SSC 333 is the model number of this chip. That's very important because that allows us to pull up its data sheet, which we have right here over on the computer. And so in this data sheet, we can go over on the side here. Let's blow this up a little bit. That does not make the side bigger. So we're going to go to this pin diagram, and from the pin diagram, again, this is the fast version. We went over this in a little bit more detail in the first video, but we found that down here on pins 23 and 24, we have the UART TX and RX pins. And we measured with our multimeter, and we found that it was, a standard 3.3 volt UART. We discovered that the baud rate was 115, 200, all standard stuff we're dealing with. And that means that we can use a cable like this, a very common 3.3 volt UART to USB cord, in order to connect up to that UART interface and to interface that UART with our computer. So that's what we're going to get set up, and then we're going to show the problem we have with getting a persistent shell, and then we'll discuss how we're going to overcome that. Just want to set the stage. So let's go over to our microscope. So you saw in the wide shot that I have these kind of pogo pins. These are called PC byte probes. I'll definitely I have a link to these in pretty much all my videos. If you look through for just in those Amazon links, buy it wherever you want. I don't really care. But I'm gonna connect up. So here, down here, I have the TX pin, and I'm connecting that to the RX of my UART cord, because you have to flip-flop those signals. And then I'm going to, okay, that got knocked off a little bit, but that looks good. And then off camera, it's kind of hard for me to show, I'm also connecting a third up to ground that's just kind of on a little screw hole. Did I knock that loose? I probably did. Let's get those set up. That looks pretty good. So now I don't have the device powered on yet, so we can go over to our computer. And here I have just a very standard command using PicoCom, which is a terminal emulator. And then you can see at the end of this command, I'm specifying dev TTY USB 0. So USB 0 that on that TTY path there is usually where on a Linux system, this USB to UART cord is going to show up as. And if you have multiple of them, it'll be like USB 1, USB 2, USB 3, if you have more than one of those cords. So then you can see the -B flag. We're specifying that default baud rate, that most common baud rate that we find on these embedded Linux systems. And now it is ready to start interacting with our UART terminal. And so I'm going to power on this device, and we're going to cross our fingers, and it looks like we have at least the TX of the board connected to our RX pin, and then we're going to observe the boot process of this embedded Linux system. And so once it boots up, we're just going to start hitting enter, and now we can see that we can in fact confirm that the other pin is also connected, right? So by receiving meaningful ASCII, text-based data, we can confirm that we are receiving data, and we can transmit data by hitting enter. Now you can see here, it'll say login, right? So it's prompting us for a login. And if this wasn't, sending so much data, scrolling by so fast, sometimes this slows down on this device. What you would find out is, like, I can put root, and it will never prompt me for a password. It'll just say login incorrect. So this device is not really even set up to prompt properly for a password. There is actually a hard-coded password hash, as we discovered in the last video, but we're not able to actually use that. Even if we were able to crack that password, we're not actually able to log into the system because it's not actually ever prompting us for the password. So there's another problem that we discovered when we did the bootloader glitch. We discovered that the underlying file system is squashfs. Well, what's the problem with that? Well, that file system, which we're going to see here when we take the chip off and remove the firmware, that is a read-only file system. You can't mount it as read-write. It can only be mounted as read-only. And so because of that, we're going to have to create a new squashfs file system to do our firmware modification. So I'm getting a little ahead of myself. Let's go back to the desk. And what I'm going to do is, let's just spin this out of the way for a second. Going to remove all my cables. I'm going to power off the device because that would not be smart to do all this on a live running device. I would never be that dumb. Actually, I did that in my live stream, if you watched that. All right, so we're going to go into the microscope here, and let's just get it situated so we can see right there. We got our flash chip. And so the first thing I'm going to do is I'm going to take some heat-resistant tape here, and you can kind of see right here there's this plastic connector, and there's another connector here. And what I do not want to do is start melting this plastic when I am throwing heat at our flash chip. And so I'm just going to tape that off, and that will shield all of those components from the heat, which we are now firing up our heat gun. I'm going to turn on the hot air extraction just to be safe, and got to grab my tweezers. All right. So full disclosure, I have been doing a lot of soldering and desoldering of this chip. And so this should come off pretty quick because it is not the original solder. So there we go. Set that aside, and there is our flash chip. And so we could clean up this chip, but I have noticed that I can just stick this right on the reader, and I've had basically no problems doing that. So what we're going to do is I'm going to prepare the socket of our programmer. And so right here you can see the socket. I'm going to press down. And yeah, we're way out of focus, but let's get that in focus. There we go. And the nice thing about having a microscope is not necessary to do this work, but it just lets me do some extra verification like this to see that, in fact, there is no solder being bridged and that I do have a good lined up connection from the chip to my socket. And then we will come out here, and here I have my Xgeku T56 universal programmer, and I'm going to place this chip pin 1. So pin 1 with the little circle is facing up inside of this reader, but we're going to put it all the way to the bottom of the reader. So we have a pin 1 indicator saying that pin 1 in this reader's orientation is up top. And so the way it wants us to put this in here is all the way down at the bottom. And then we're going to lock it in place and turn it on. And now we are ready to read. So, take these gloves off for a second here. All right, so now we're back over at our desk, and I'm going to grab another console here. And so first, I'm just going to reread the firmware out of this flash chip just to show you that we can do it. So in previous videos, a lot of the times what we've used is the official software that is a Windows-only piece of software provided by the creators of this piece of hardware, this universal programmer. That's called XG Pro. And so that software is Windows-only, it's closed source, but there is a really awesome project that I featured in one of my recent videos here called Minipro. And they have released a kind of beta, very bleeding edge feature that supports the T56 programmer to do firmware reading and writing. And so we're going to use that today. So it works natively in Linux. It's all open source. Very great. Don't have to run sketchy Windows binaries that probably make calls out to other countries. Not going to do that. So over here, what we're going to do is we're going to run Minipro, and then we're going to specify the chip here. And so this is the model number, and then the configuration of the chip. And there are command line flags in the Minipro program to search for all of the chips that it does support. So very cool stuff. And then what we're going to do is we're going to do read, and then we're going to just say, firmware.bin. And it says the chip ID is okay. This is all a good sign. This is happy because usually if it can't read the chip right, it'll fail at this spot, and it'll say, oh, chip ID is all zeros. Do you want to continue, right? So it looks like it read the chip just fine. And so I'm going to list these files, and I already actually have a firmware read that I did previously. So actually, just as a quick sanity check, let's just MD5 those. And interesting, it's not the same. Now, I think I'm actually okay here, and I think the reason why these might be different, oh, you know what? Okay, I actually don't know. Let's figure out why these are different. So this file right here is like the first time I ever read the firmware off, and since then I've been doing firmware modifications, but I thought that I put this firmware back on there. So let's actually see what the difference is. Oh, really? Okay. It wants this to be smaller. Okay. And then we can say enter to find the first difference. All right. Okay, so there's there's actually a ton of differences. All right. Well, fun times. All right, so we're going to just work with this this firmware that we just read. We'll modify that one. All right. So fun adventures here. All right, so what we're gonna do first is we are going to run binwalk on this. Let's get this size a little bit bigger, although binwalk might not like that. Okay, so let's just run binwalk. We're not gonna run the -e flag to extract anything. We're just gonna run binwalk. And yeah, like I said, it doesn't like, all right, I'm sorry for all you people on mobile phones. We're gonna reduce the font size for just a minute. So what we're gonna find in here is we're gonna find 2 SquashFS file systems. And I'm not going to go into this in too much detail, because if you are practically doing this, you could just, guess and check. You could modify one of them, see if it has the effect you want. If it doesn't, try the other one. But I can tell you the one we want to modify is this first one. And part of the reason, yeah, let's go ahead and run the extraction. And what we'll find is if we go in here, I can make this font bigger for you guys now. Let's let's grep for a password. I'm looking for the password file. We'll notice that it only shows up in the file system that's at that offset. So that's the first squashfs file system. That's why I know that's the file system I want to target. That was a roundabout way of telling you why that's the one we're going to modify. All right, so again, let's go to binwalk. So I'm typing binwalk v3 because I have both binwalks installed on my system so that I can compare and contrast the old Python-based binwalk and the new Rust-based binwalk. And so I definitely would encourage everyone to try out the new version of binwalk, but that's why I'm typing v3. You don't have to type that. All right, so let's just print this out again, and let's see that this squashfs file system right here, okay, it's at this is the offset in decimal. So this is the offset in hex, and this is the offset in decimal of where that file system is inside of the whole firmware blob, right? So inside of that firmware at a specific offset, that's where this squashfs file system starts, where our root file system starts. So I'm actually just gonna kind of take notes of this stuff down here, because that's gonna help us build out our dd command that's going to carve just the file system out, and then later we can put it back into place. And so what we're gonna do is we're just gonna write that down. And then the other piece of information, so that tells us where the offset is, and then we wanna know how many bytes the squashfs file system takes up. And binwalk parses that from the header in the squashfs file system, and it will show us right here that this is the image, yeah, it says image size this many bytes. And so we are going to write that down as well. And so then what we're gonna do, so we have that firmware file. Now we want to carve out of that firmware file just the squashfs file system. So the way we're gonna do that is with the dd command. So we're gonna do dd infile equals, and that's our firmware, and then out file, we'll just call it the root fs.bin, and then now we have to specify which bytes we wanna extract. So the first thing I'm gonna do is say block size equal 1. So that's the unit of data that I'm dealing with is just 1 byte. Then I can do skip equals and our offset, and then count how many bytes do I want to copy out of the bigger file. And so that's going to be this length right here that we extracted, that we got from binwalk. So all this information came from binwalk, and so now we know exactly how to carve this file out. We can hit enter. It'll take a little bit. It's not super efficient because we're doing it 1 byte at a time, but it's not that big of a file, so that's fine. So now we have this root fs.bin file, and we can sanity check that we carved out the right file because we can run the file command, and directly at offset 0, it finds the squashfs header and is able to parse all that information. We are on the right track. Now what we're going to do is run the unsquashfs file system to unpack this root file system. So we do that. We have squashfs root, and here we can see the root file system on this device. So now we need to make our firmware modification. There's a lot of different ways we could do this, but the key file I'm going to make a modification in is etc inittab. And so looking inside this file, what we see here in this bottom line is we see ttys0. That is the kind of default serial terminal interface on a Linux device. And then what we have at the end here is bin login. So on that console, when it gets launched, what is it going to execute? It's going to execute bin login, and that's where we get prompted for a login. And because of a whole bunch of reasons, we are not able to actually log in. But what we can do instead of having bin login, we can just run bin sh. That will just drop us straight into a shell with no login prompt when we have access to that UART interface, which we have over on the desk. So There we go. We're going to save that file. We're going to back out of there. So now this squashfs root directory has been modified. Now we want to repackage that into a squashfs file system. So what we can do is we can run make squashfs, and then we can specify the directory. And then we can say, you know, okay, we're going to specify the file. And so we're just going to call it new root fs.bin. And we get in and hit enter, and now it has created this other file here. But let's go ahead and look at this, because if we look at the file signatures, we're going to see, so we're going to see a problem here. So in the new file here, well, first of all, the first reason why it's wrong, let's look at the sizes of these files. So the original root file system was 2.4 meg. And this one is bigger. It's bigger by like a decent amount, right? So it is, you know, 0.4 meg larger than the original one, which is going to be a problem if we want to copy it back into place. It's going to be too big. And so the reason why that is if we run the file command, we'll see that the compression library is different between these two files. So the new one that we generated used zlib, and the one that was originally on the device used XZ compression. So those are just two different ways to compress files, and for whatever reason, XZ was able to get it smaller than zlib was. So what we can do is we can also use that. So we're gonna delete that file, and then we're going to bring up our command again, and all we're gonna do is do -comp for compression XZ. And now it is going to make a new squashfs file system that uses that same compression type. This is also important because it's possible that the kernel or the underlying system might not support a different type of compression, and it might kernel panic because it doesn't have the references to those libraries, right? There could be a whole bunch of dependency problems. So that's why when we recreate a file system, we want to have it match as closely as we can in all the file system types, the compression types, any other configurable options. We want to get it as close to the original as we can. And so that we are able to do. So now what we're going to do is we're going to copy our firmware, and then we're going to, this is the full firmware image. So this is not the thing we just created. So we're going to go back to that firmware image we read out, and we're just going to call this new firmware.bin, making a copy. And then now what we want to do is we want to take our new file system and place it into the correct spot. We want to copy it over top of that original root file system. So to do that, we're going to do another dd command. We're going to say dd infile. So in this time, our infile is our new root file system, and the out file is going to be this new firmware. Okay, so we're copying the new root file system into the new firmware. And so now what we're going to do is we're going to say seek, and we're going to do that same offset number. And then we have the same command here, which is, by the way, this would mess up if I don't do block size equals 1. So count, same as last time. Now we need to add an important piece called no truncate. And so what this is going to do is, because the two files are of like different size, is it's going to have the original file here, new firmware. It's going to keep everything after we copy in the new root file system. It's not going to just like stop at the end of the squashfs file system, because there's other data after that in the new firmware that we're not modifying, and we want it to keep all that. So no truncate is what this little option stands for. So we're going to run that command, and then in a little bit, dd will come back and say, awesome, you have a new firmware image. Let's just do a sanity check here, because the first time I did this, I did not do that no truncate command, and I had a completely messed up image, and I flashed it back to my camera, and then it just wouldn't boot. I had no UART output at all, and I was like, why is this? It was because I like overwrote the U-boot bootloader and a whole bunch of other crap. So it's always good to sanity check as much as you can before you go do the physical part on, you know, like soldering and desoldering stuff. Do an extra sanity check, take your time. So to do that, we're going to run binwalk. Gosh. Okay, I have to run it with the font as small as possible. So here we go. We have got, all right, yeah, this is the same, and at the correct offset is where our squashfs file system is. Let me just confirm that this looks the same. Okay, yep, it looks the same as our original firmware. So now we have that file, and now we want to write it back to our chip. So, all right, we can go bigger font now. We're gonna say Minipro-P, and again, I'm gonna copy over this, this part number for my flash chip. I think, oh, here, I'll show you guys this. So I think like -L, no. Let's, oh, of course, they don't make help. It's only in the man page. List all supported devices. Oh, you're like, oh yeah, oh, so what you can do is if you like have part of the serial number for your chip, let's just say XM25Q. Let's say like that's what there's all the chips that match XM, the start of XM25Q, right? So that's how you can look through all the chips that are configurable for you. So I'm going to pick the chip that I already know is the correct one, and then we're gonna, instead of -R for reading the firmware, we're gonna do -W for write, and then we have new firmware, that new firmware file that we have procured, and we're going to run that. It's going to erase the chip first, and so I'm just gonna zero everything out, and then it is going to write our firmware. Again, it's reading the chip ID. That means we probably have a good solid connection on here. I want to say this open source software right here is a huge improvement already on the original software. And that's because right here, this erase operation that took 23 seconds, like most of the time in the XG Pro official first party software, it will fail, but it's not true. It's not a true fail, but it will error out, and then you will have to close down the complete program and reopen it, and then run a blank check to verify that, oh yeah, the erase operation did actually succeed, and I can go ahead and do a write with the erase disabled, right? So this software is already better than the original software just for that alone. It's so easy, it's worked every time, it hasn't crashed on the chip erase. So there we go, it did a verification on our code, it all succeeded. Now let's go back to the desk, and now we can put this chip back on the board. So let's go over to our desk. All right, I'm gonna put some gloves back on because I may or may not throw down some flux just to make sure that the chip gets on in a good way. All right, well, before I do that, let me grab the chip. Don't need our reader anymore. And let's get this front and center. All right, so we're looking under the microscope. Whoa, that's really zoomed in. All right, so there is the location that we want to return our flash chip to. Let's just throw just the slightest amount of flux. Don't need a lot. Not trying to start a flux company here. All right. And then I want to position the chip correctly. Let's get this in focus. So right here, we can see a little circle. That is the pin 1 indicator. And so we need to actually flip this chip around, grab it with my tweezers, and then place it like that. All right. Now I'm going to bring my hot air over here, and let's start heating it up. There we go. Oh yeah, slides right. Oh, there we go. Slides into position. Perfect. That's how you know. All right. Perfect. We're gonna let that cool down. I can turn my air extraction off. And let's just go back to, oh wait, actually, no, I need the microscope still. Well, okay, I'll show you guys what I'm doing. Okay, so now I'm flipping it back over, and so just because you couldn't see the first time, so this is where I put my ground usually. It's just an easy spot to connect it up. There might be an easier way to do it, but this is the way that I do it. So here we go. All right, let's get this connector. This one might be better to connect first. All right. All right, shaky hands. All right, there's TX and RX, and then very carefully out of camera, I'm connecting up ground, and then we're gonna verify it looks like we're good. Let's get that a little bit better. You can see that I've been poking at these traces a bunch because I've like chipped some of the solder away, which is kind of funny. All right, there we go. Looks like we have a solid connection. All right, let's go back to our screen. This is the moment of truth. See if our firmware mod has worked. All right, so there's our console. We're going to power the device on. All right, so at least one of, okay, we didn't brick the device. That's good. No bricking has occurred. It's booting, all right. This is good, this is good. All right. We are booting into Linux. All right, moment of truth. We have a root shell. All right. And run ID. And we can see that now all this stuff is scrolling by, right? Before, when we got in via the bootloader and we got that temporary root shell, you noticed in the video, I was expecting all this stuff to come scrolling by, but it wasn't. And so I think there might be a way in that temporary shell to get it to properly execute the whole init system and actually start the software that runs the important business logic of the camera. But for some reason that didn't happen. But it's much better to have a persistent situation like this than always having to go in through the bootloader. And so now we have a shell, we can run PS, and we can see all the programs that are running here. So, so here we can see, okay, cool, we can see that NTP, it's reaching out to time.nist.gov for its time. Oh, cool, we see an RTSP daemon, so that's going to be a video streaming server, so that's pretty cool. I wonder if I can run netstat and see. I literally haven't looked at this part yet, but I'm guessing that we'll find something on a common RTSP port. All right. Cool. So definitely a bunch of stuff to explore now. All those binaries, especially like anything that looks custom and proprietary, right? There's one, yeah, I mean, we're seeing a bunch of logs for something like security, IoT, TP-Link. The UART is kind of getting screwed up here, but I would, oh, here we go. So this bin cloud IoT and bin, all right, now it's gonna keep, scrolling by on me. All right, so there's definitely some custom binaries here that these are the types of binaries that I would look to target my reverse engineering at, right? So extracting those binaries out and reversing them. And now that I have a live device, I can interrogate the device as it's running. I can see files that are being read and written to on the device, and it gives me a much clearer picture as someone who's looking for vulnerabilities on an IoT device. So thank you for watching this video. If you watched to the end, I really appreciate it. Leave a like and a comment, please, and tell me what you like, what you don't like, what you want me to do next. I got nothing else for you. Have a good day.